so you can.
This meeting is being recorded.
Right. Okay, right. So, oh shit! Now something bad happened. Okay, so yeah, RFF has been doing this structured expert judgment on the social cost of carbon for about 2 years, and there's some publications here. I'm not going to go through them, just point out that they're there if you want to look at the information. Now, one of the things we did differently on this solicitation was to make a little video as an introduction to structured expert judgment. And I think this worked really well. It saved a lot of time in the elicitation. And the video is just 10 minutes, and people find it a fairly harmless way of being introduced to the subject. So that's something we're going to keep using. And this, by the way, this is a link. You can run the video, watch it. You can download it from my website. I'm showing one sheet from that video just to give you the idea. You see here 6 studies, starting with the ice sheets at the University of Bristol. And for each study, there's 4 calibration variables. And so we explain what these range graphs are. This is a 90% confidence band. The circles are the median, and the red thing is the realization. And we just walk through this and show them the good, the bad, and the ugly about structured expert judgment. So here, for example, we illustrate high information and low statistical accuracy, right? So being very sure of yourself is not a predictor of quality of your response.
Roger.
Good. Yes.
We only see your first slide. You might go through this, but we don't see it. We only see the first slide. So shit, I think we need to, yeah.
What can I do?
Let's try to stop sharing.
If I go out, can you see this now?
Now, yeah, we can. Yeah. But try to move between slides now to see.
Okay. Well, can you see this one?
Yes, but yeah, okay. So indeed, clicking on the slides.
So the presentation mode doesn't work.
So it looks. Yeah. We could try to stop sharing and reshare again, or you can just click on
look,
that,
I can go on like this.
Yeah, okay, great.
So this is where we were, just these things. It becomes very visual. Yeah, is okay?
Yeah.
Okay. This is the Goldilocks solution, high information, high statistical accuracy, and so on. And so now I go to the actual study. There were 2 panels, one on economic growth and the other on future emissions. All of these are projecting these quantities out to 2300, which is a leap of faith. And in general, we're interested in predicting what they call the frontier economies, this is basically OECD, and predicting the rest of the world, which is trying to catch up with the frontier. And according to economic theory, that should all converge at an exponential rate. And of course it doesn't. And so there's a whole lot of things that are interfering with this convergence. But this has a big impact on what we're going to be doing to the planet. So a lot of these calibration variables have to do with how well some of the other countries or how quickly they are converging into the frontier. So this is economic growth. I'm not going to go through all of these, just to show that they're there. And now, if we look at the range graphs for this panel, you see this is really very homogeneous, very consistent. Looks very good, and it is good. So especially when you compare to those 6 things I showed you on the first slide. So the second panel was future emissions out to 2300 for CO2, methane, and NOx. And again, a lot of the calibration variables have to do with convergence to the economic frontier. And you see here also quite good, not as good as the previous panel, but really quite consistent. And so these economists really nailed it. I mean, this is one of the best panels that I've ever seen in terms of these indicators. So if we look at the scores, this is the economic growth panel. These are the statistical accuracy, what we used to call calibration, which engineers don't understand. Well, that's the problem. They do understand it, and they don't understand why we're even here. But yes, so and what you see is, wait a second, we're not looking at the whole sheet here. Yeah. What you see here is that we chose as the performance weight a statistical cutoff at 5%. So everybody above 5% was weighted, and we had 1, 2, 3, 4, 5, 6 of those people, and there's one more who was actually above 1%, but he wasn't weighted. So this is a large number of good experts, and what happens in that case is you don't see that much difference between equal weighting and performance weighting because they're all good, right? And so this is a very typical picture. Performance weighting is scoring a little higher on statistical accuracy and almost a factor 2 more informative, which is worthwhile. So, I mean, the really short explanation, as in that video, is that the performance weighting is designed to give more informative assessments, narrower confidence bands, without sacrificing statistical accuracy. And that's exactly what we're seeing here. So if we go to this one, oh yeah, so this thing was supposed to appear as an animation, but here you see, again, the experts are all, not all, but most of them are quite good. So we had 19 experts in total, and 13 of those 19 had statistical accuracy above 0.01. So if we look at the whole data set that we have collected over all these years, there's about 33% of the experts score above 0.01. So here it's much, much higher. And one of the results is that there isn't a hell of a lot of difference between performance weighting and equal weighting. And among the performance weighting, so this here, for example, is global weight with optimization. This is global weight without optimization. And they're both quite good. I mean, these scores for statistical accuracy are really equivalent. And you have to realize that if the expert or the model is statistically accurate, these numbers will be uniformly distributed on the 0-1 interval. So nobody's going to make a fuss about any of these numbers. And the informativeness is also quite good, but equal weights is a little worse, as you might expect, but still quite decent. So that's the picture on the performance from these panels. Oh, this slide was hidden. I decided not to show it, so I'll just skip it. Now I'm going to show some of the results. And in a way, it's a lot of what you would already expect, but there are some significant surprises in here too. And I want to compare it with what people have been doing previously, which is what the IPCC calls the shared socio-economic pathways. So these are a bunch of storylines. You probably heard that term. That's a poor man's way of dealing with uncertainty. You just make a lot of stories and tell the storyline. And so here are these things, and then people use these storylines to capture the uncertainty, which of course it doesn't do. And there is no probability associated with these things, and there's a big discussion. Should we give them equal weights? Should we give them differential weights? And nobody knows what they're doing, but that enables you to go on talking forever, and that's what they do. So now we have a really defensible quantification of this uncertainty. And you see it's following the general picture, but there's some interesting things. First of all, these 4 pathways do not cover the uncertainty range, right? So this light gray is the 1% to 99% quantile, and the dark gray is 5% to 95%. And so what you see is there's a lot of uncertainty outside these pathways. And in particular, let me point out this. Look here, this is 0. We're talking about the cumulative growth from 2020 out to 2300. And if you look at this 0, you see, holy shit, there's 5% probability that the cumulative growth for the next 300 years will be negative. I repeat, there's a 5% probability that the cumulative growth for the next 300 years will be negative. Now, you will never get a statement like this from the Bogsat method. You know, the Bogsat method is a bunch of guys sitting around a table. The IPCC will never, ever tell you that there's a 5% chance of negative growth out to 2300. So this is an example of the sort of thing that you get when you really quantify the uncertainty and do your best in trying to, because the economists are very clear about this. Yeah, this can happen. And whereas there is this myth that things always grow, but they don't believe it. So this is projected total atmospheric CO2 concentrations. Same idea. These are the shared economic pathways of the IPCC. This is the quantified uncertainty from our study. Yeah, you see that it looks like it's going to stabilize, or the median value stabilizes around 500, which would be great if we can do that. But the uncertainty goes out to over 2000. So this is not a happy picture. And you don't want to just look at the median, you want to look at the whole uncertainty. And then the next one gives us the annual emissions from the shared socioeconomic pathways. And this is interesting because what these guys do here is they just make, for example, for this aggressive growth scenario, they make, this is sort of business as usual. If we don't do anything to reduce emissions or mitigation or anything, we're going to grow like hell out to here. And then they just assume, well, look, that nobody's going to keep doing that because we'll all be dead. So one way or another, it's going to go back down, right? And they just draw a straight line back here to 2250 and said, we assume it's all zero emissions in 2250. There's no story about that. It's just a bold assumption that they impose on all of these things. So what we're seeing here is that the median does indeed go down, and we're looking at zero, pretty much zero emissions from, say, whatever, 2150 on. But we don't see this behavior at all. And this is the reason that a lot of people don't want to take these socioeconomic pathways. Industry trying to figure out why this isn't what you want to do. All right. One more, global mean surface temperature. This, the shared socioeconomic pathways, this is RFF. So you see the median is going up to about 3.5, which is not a happy number here at all. But the 99th percentile is going up to, right? Then we're all dead. So that's what this is telling us. There's no nice way of bringing that message. All right, so let's move on. I've got to figure out what I'm doing. Okay. Now, so this was the main part of my talk, and here the animation was important, but it doesn't work. So the random expert hypothesis. So frequently heard statement from certain quarters is that, well, yeah, sure, you can measure these things on a panel, you know, but it doesn't mean anything. I mean, you're just measuring the noise, right? So experts are always going to differ, but will those differences persist? Oh, you know. So fact is, we can actually test that idea. And here's how we do it. We have the original panel. There's 3 experts. Actually, maybe I can just move this guy away. How's that? Yeah. Oops. Oh, it didn't work. Yeah. 3 experts. Now, and they have assessed 3 seed variables. So just to give the idea, yeah, they're different, right? This guy, you know, just had a divorce, right? So he's preoccupied. This guy has a stomach ache, so he's not feeling good. This guy just got a big grant proposal accepted, so he's super confident. So that will explain the differences in their behavior, but we can test that. So how do we test that? We can scramble these assessments. So let's assume we make a new expert, random expert number 1, and he gets the stomach ache from the blue guy, he gets the divorce from the orange guy, and he gets the grant accepted from the purple guy. So we are redistributing these random stressors, right? And of course, we don't do that once, we do that 1,000 times. And now we look at panel-wide metrics, like the average statistical accuracy over the whole panel. And the random expert hypothesis says that this original panel could just as well have been any one of these panels that I generated by this random scrambling. Note that if I use equal weighting, the equal weighted combinations are exactly the same for the scrambled panels and the original panel, right? So those performance blind methods are invariant under this scrambling. And the idea of performance weighting is that there is an expert effect, right? Some experts are better than others, and we want to find the good ones and go with them. That's a different philosophy. So the random expert hypothesis says that the original panel is just a sample from this distribution that I get by scrambling, right? And so that means that if I look at the quantile of, say, the maximal statistical accuracy, the best expert in the original panel, I look at the quantile that he realizes in this scrambled distribution, that should be uniformly distributed on the 0-1 interval, right? That's what it means, right? So if we look here, this is what 49, so we have 49 studies. If I take 49 uniform variables and just plot them around the value 0.5, this is what you're going to see. You're going to see about as much color above this line as below this line, statistically, right? That's what it would look like if the random expert hypothesis were true. This is what the data looks like. So this is a picture that was prepared by Denish, who's on this call, I see. So this is not uniformly distributed, right? And we are looking at 4 panel metrics for statistical accuracy. We have other ones for informativeness and so on, but they're all basically like this. So for statistical accuracy, 49 studies, here they are, right? And we plot just the quantile of the original panel that is realized. No, I'm saying that wrong. We look at the quantile within the distribution of the scrambled panels that is realized by the original panel, right? And that thing should be uniform. And you see it obviously is not. And so this is a very powerful test. So the hypothesis that all of these guys satisfied the random expert hypothesis is rejected at 10 to the minus 12. So that's just obliterated. I mean, it's there's you know, it was already clear, right? But now it's clearer than clear. Now, there's one thing I want to point out here, and that's this minimum. The minimum is this orange. And I reversed the sense of the minimum because I want the results that are unfavorable to the random expert hypothesis, I want to be above the line of 1/2. So the idea is if there is an expert effect on the minimum, then the worst expert in the panel is going to be worse than anything that you can generate by scrambling them around, right? But then he would be here at the bottom, but I want him at the top. So I take 1 minus that and plot that up here. And so now you can say the amount of color above the line says that the random expert hypothesis is not doing very well, but especially the minimum. And this is something I've never really thought about, or only tangentially, but now it really kind of hits you in the face that the expert effect is actually strongest at the low end. So this scrambling has most difficulty in reproducing the behavior of the worst experts, right? There's a deep philosophical truth there somewhere, and I haven't found it yet, but it's something to think about. So let's look at this one here. For example, this is Gerstenberger's study on the Christchurch earthquake. And this says that 75% of the minima in the scrambled panels were better than the minimum in the original panel, right? That only 25% of the scrambled guys did even worse in the minimum than the original minimum, right? So if we reject the hypothesis, that the random expert hypothesis for this individual study, we have a 25% chance of making a false rejection, right? That's what the p-value means, right? So if we add up all of these p-values over the whole set, you will find that if we reject the hypothesis for all 49 studies, we will expect to have 10 false rejections. okay? Because look, the random expert hypothesis is sometimes true, right? I mean, if all experts are equally good or equally bad, it might well be true. The random expert hypothesis is going to fail when there are big expert differences, right? So what this is saying is, well, in 20% of the cases, it's actually not bad. Right? Surprise, surprise. So yeah, that's what that says. And okay, so now I turn to our study, and our study sort of reinforces this because we had a lot of good experts. So you wouldn't expect, after you think about it, you wouldn't expect that the maximum statistical accuracy or the average statistical accuracy would be such a big signal, right? It won't. So if we look at our two panels, the economic growth scenario and the future emission scenario, statistical accuracy and informativeness. I'll just go through one of these to explain what it's doing. So the average statistical accuracy for the EGS panel was 0.23. The standard deviation of statistical accuracy was 0.23. And the maximal statistical accuracy score was 0.71. The minimal statistical accuracy score was 3 times 10 to the minus 4. Here you see the minimum is, is stepping out of line. So if we do these 1,000 scrambles, what we find is that 14% have a lower statistical accuracy than the original panel, right? The rest are all better. So there's no signal here that there's a strong expert effect with respect to the average statistical accuracy. Same with the maximum. It's a little bit higher, but it's still not anywhere near being, But you look here at the minimum, this says that 91% of the scrambled panels had a worst expert who was better than the worst expert in the original panel, right? So that in itself is not quite statistically significant, but it's getting there. And if we look at informativeness, it's 100%. So the very informative guys are the ones typically who are very inaccurate statistically. So there's a correlation there, but it turns out that the informativeness, 100% of the scrambled panels had an information score that was worse than the minimum. The lowest information score was lower than 100% of the scrambled panels. That means there was somebody in the original panel who was super uncertain, and we couldn't recover that by scrambling. So that's an expert effect, right? And similarly for the future are significant for that particular study. So again, the message is the random expert hypothesis might sometimes actually be true. And when it's not true, it seems to be the case that the scrambling has more difficulty reproducing the really bad experts than reproducing the good experts. Okay, I think that's about it. Oh yeah, no, there's a couple more things. We compare this with the cross-validation studies that we started doing around 2016. It took a lot of work, by the way, and a lot of coding, and the code takes a long time to run, and it's just a pain in the ass. So if this new technique really is equally or more convincing, that's really a blessing. So what did we do? We took these 49 studies after 2006, and we set the training set equal to 80% of the calibration variables. This was just done by some experimentation. And we take all subsets of 80%, and we initialize the model on that subset, and then we predict the remaining variables, which is maybe 2 or 3 or 4. And then we plot the unnormalized weight of the performance-based decision maker over the unnormalized weight of the equal weight decision maker. So, and here is 1, and this goes from a 10th up to 10. And so if these lines are above 1, studies for which the line is above 1 are studies in which the performance weight outperforms equal weighting on this cross-validation. And so you see that's this picture, and you reject the hypothesis that these two are really equal, at the 3 times 10 to the minus 8 level. So of course it's massively rejected, but it's less powerful than the random expert thing. Why? Because you have this intermediary of making the weights and combining them and comparing the performance of the combination versus the performance blind combination, right? So it's kind of an indirect way of getting at what you want, plus the fact that this 80%, 20% split means that in your testing set has very low power to discriminate between these two guys, right? So cross-validation, yes, it was certainly worth all the effort that we put into it, but this random expert hypothesis looks like a much easier way to make the same point. Okay, so there is this website on structured expert judgment. The idea is that we're going to fold all this into a website that will be at the TU Delft, right, Tina? I think, yes. But for the time being, you can go here. There's lots of funny stuff here. And that's it. That's any questions? This picture will be familiar to some of you. I'm not going to explain it, but I'm stopping now. Is that okay? Yeah.
Yes. Yeah. Thank you, Roger. Just also let me add, because on your website, right, it's also there's plenty of information there, and with the videos and so on. And
yeah.
Denise also pointed out in the chats references to well, the extra, like all the analysis for the slides that you showed on the expert random expert hypothesis. I see some questions.
May I add that,
Sure.
Denise, I did this in Excel, and I'm not going to show anybody my Excel